Welcome back to the deep dive. You might remember we took a plunge into the fascinating world of quantum computing with a review article not too long ago.
That's right.
Well, you, our curious listener, have brought us back for a third look at Prashant's, a study on the basics of quantum computing. Still labeled as layman's perspective, but
Yeah, but as we found out, it really does go quite deep, doesn't it?
it absolutely does, beneath the surface for sure.
And this report from the University of Montréal, it's valuable because it really tries to break down these fundamental ideas. Quantum computing, information processing.
It really aims on.
It does. It starts from, the huge impact quantum theories had and how central information is in physics now. It kind of sets the stage.
Okay, so for this deep dive, the mission, if you choose to continue accepting it,
It sounds serious.
is to come out with an even stronger grasp of these core quantum concepts. We want to really shine a light on why there's so much buzz, maybe spark a few more aha.
Moments. That's the goal.
We'll be looking closely at the history, the limitations of classical computers, which, interestingly, kind of paved the way.
Exactly. Necessity and invention.
And those truly revolutionary principles that make quantum computing, well, potentially revolutionary.
And just to map things out quickly, we'll cover quite a bit. The history, how we got here, then the classical computer limitations, which, as you said, leads naturally into superposition, entanglement, those core ideas.
Mind-bending stuff.
Definitely. We'll touch on quantum teleportation too, thermodynamics, the actual experiments trying to build these things.
Oh, wow.
And even some of Prashant's more forward-looking thoughts on quantum mechanics itself. So, yeah, ready for round 3.
Absolutely. Let's dive right in with chapter 1, the genesis of computation. Prashant traces this amazing evolution, gears and levers,
Mechanical beasts, yeah.
all the way to the tiny silicon chips we have today. It's quite the journey.
It is. But what's really insightful, I think, is his point about the underlying similarity.
Right, how different they look,
But fundamentally, whether it's cogs turning or electrons flowing, classical computers are just manipulating bits, zeros and ones.
binary, foundation. And then he brings in Moore's law. We all know that one. Processing power doubling.
Roughly every couple of years, yeah.
But the crucial link he makes is to the physical size shrinking. We keep packing more in, and the space for one bit gets smaller and smaller.
Down towards the atomic level.
Exactly.
And that's where things get really interesting, because classical physics just doesn't cut it at that scale. You need quantum mechanics.
So Prashant argues, as we keep shrinking things, quantum effects aren't just a nuisance. They become the dominant factor. Our old models break down.
They really do. You can't ignore it anymore.
And here's the kicker. He stresses this isn't just about making things smaller. It's not just super miniaturization.
No, it's a whole new way of thinking about computation, a new paradigm.
It's about using quantum mechanics itself to create entirely new algorithms, things classical computers just can't do.
Precisely. That's the real potential. Outperforming classical machines on certain types of problems. Problems that are just intractable today.
Like impossibly hard problems.
Problems that would take a classical supercomputer longer than the age of the universe to solve. That kind of hard.
Wow. Okay. So what makes a quantum computer so different fundamentally? Prashant highlights a few key characteristics.
Yeah, several important ones. First, memory capacity. It can be exponentially larger than you'd expect from its physical size, because qubits can be 0 and 1 at the same time.
That superposition thing again.
Exactly. Second, manipulating inputs. A quantum computer can, sort of, work on a huge number of inputs simultaneously. Quantum parallelism.
Which is completely different from step-by-step classical processing.
Totally different. And third, the computation happens in what's called Hilbert space, a complex, multidimensional mathematical space, not just simple zeros and ones.
Sounds incredibly powerful, almost sci-fi. But then the big question Prashant raises, can we actually build one?
The feasibility question. Yeah, is it just theory or can we make it real?
That's the billion-dollar question, I guess.
Or maybe $1 trillion. And we'll definitely get to the experimental side later. But first, Chapter 2 gives this great literature survey. It walks us through the history and the key ideas.
Right. Section 2.1, a brief history. It wasn't an overnight thing, was it? It started back in the 70s, early 80s.
Yeah, a gradual evolution. Figures like Bennett, Benioff, Deutsch, Feynman, pioneers from physics and computer science asking, can we do better? Can quantum mechanics help?
And Feynman's idea in '82, that was huge, wasn't it? Not just faster calculation, but using quantum systems to simulate other quantum systems.
That was the key insight, simulating quantum physics problems, especially these complex many-body problems.
Why was that so significant?
Because classically, simulating those interactions gets exponentially harder as you add more particles. It becomes impossible very quickly. Feynman saw quantum computers could potentially do it polynomially, much, much faster, a natural fit.
And then David Deutsch took it even further in '85.
Right. Deutsch realized it wasn't just for simulating quantum stuff. A quantum computer could potentially be a universal computer, capable of simulating any physical process.
Mind-bending universality.
It really is. But, as the report notes, finding practical applications early on, that was tough. Beyond some specific math problems, it was mostly theoretical for a while.
Just an interesting idea.
Pretty much, until 1994. Peter Shor.
Shor's algorithm. That's when things really took off, right? Factoring large numbers.
Exploded is the right word, because suddenly this theoretical machine could break the encryption we rely on every day.
How so?
Well, much of our online security, public key cryptography relies on the fact that multiplying large prime numbers is easy, but factoring the result back into primes is incredibly hard for classical computers.
Right, that asymmetry.
Shor's algorithm showed a quantum computer could do that factoring exponentially faster. Suddenly, existing encryption looked vulnerable. That got everyone's attention. Global interest, funding, the whole field shifted.
It's funny, as Prashant points out, that big gap between quantum theory in the 20s and realizing its computational power decades later.
Yeah, it took time for the implications for information processing to sink in and for the right theoretical tools to emerge. Not an obvious leap at all.
So, moving to section 2.2, limitations of classical computers. This is where he explains why we need this new approach, starting with public key cryptography and classical factoring.
Right. He explains how public key systems solve the key distribution problem, like a mailbox. Anyone can drop a letter in, encrypt with the public key, but only you have the key to open it, decrypt with the private key.
Simple analogy, but effective.
And it all relies on that difficulty gap. Multiplication, easy. Factoring large numbers, incredibly hard. Classically, anyway.
How hard are we talking?
Exponentially hard. The time needed grows incredibly fast with the number of digits. Prashant gives examples. RSA 129 took months back in '94. Factoring a 1,000-digit number classically, forget about it. Longer than the universe has existed.
Our digital security literally relies on this classical difficulty.
Fundamentally. Which leads right into section 2.2.2, quantum factoring. The classical theory of computation has limits. It doesn't account for quantum possibilities.
Enter Shor again.
Enter Shor. His quantum algorithm doesn't scale exponentially. It's roughly quadratic.
Meaning, much, much faster for big numbers.
Massively faster, that 1,000-digit number. Potentially solvable in, say, millions of steps on a quantum computer, not trillions of years. The implications for breaking current crypto systems are huge, a massive security shift.
Okay, factoring is one big one. What else? Section 2.2.3 talks about searching. Grover's algorithm.
Right. Classically, searching an unsorted list of n items takes, on average, n2 checks. Find my name in a phone book with no order.
You gotta look through half of it, roughly.
Grover's quantum algorithm can do it in about the square root of n steps. For huge databases, n is way, way faster than n2, a significant speed up.
And then section 2.2.4, simulation of quantum systems. Back to Feynman's original idea.
Yeah, classical computers struggle simulating quantum mechanics, especially multiple interacting particles.
Why is that?
Because describing a quantum system takes exponentially more information than describing a classical one. For n particles, classical description scales like n, quantum scales, like 2 to the power of n.
That explodes really fast.
It does. So simulating even medium-sized quantum systems becomes impossible classically. But quantum computers, built on quantum principles, could potentially handle it without that exponential slowdown.
Opening doors for materials science, drug discovery.
Exactly. Simulating molecules, designing new materials, things we can't do accurately now. Prashant also mentions simulating quantum interference is particularly tricky for classical probabilistic machines.
Right. So section 2.3, quantum computing, a new concept in parallelism. This tackles the speed limit issue again, but from a different angle. Not just clock speed, but the way classical computers work.
Precisely. Classical computers are fundamentally serial, one step after another. Even parallel classical computers struggle with this underlying sequential logic.
They chop up the problem, but the pieces are still processed sequentially in a sense.
Often, yeah. But quantum computers, Inherently parallel. They can explore many possibilities at once.
How? Through superposition again.
Exactly. That's the key. Section 2.4 gets deeper into quantum superposition and quantum interference. A qubit isn't just 0 or 1, it's a combination of both simultaneously.
With probabilities attached.
Sort of, with complex number coefficients called amplitudes. The square of the amplitude gives the probability of finding it in that state if you measure it. He uses electron spin, up-down, or photon polarization, vertical-horizontal, as examples.
Physical examples help.
They do. Mathematically, it's a vector in a 2D complex space. He uses the half-silvered mirror experiment to illustrate. A single photon hits it.
50-50 chance it reflects or transmits.
Classically, yes. Quantum mechanically, before detection, it's in a superposition of both reflecting and transmitting. It takes both paths.
Until you look?
Until you measure. Then the superposition collapses, and you find it one place or the other.
And the double slit experiment shows this even more dramatically, right? A single photon interfering with itself.
Yes. As if it went through both slits at once. That interference pattern is a direct result of superposition. It's fundamentally different from classical probability. And that collapse upon measurement is crucial.
Okay, superposition is weird enough, but then section 2.5 hits us with quantum entanglement.
Entanglement. Probably the weirdest quantum concept. Prashant contrasts it with classical correlation, like his bank robber teller example. That correlation has a simple cause.
Makes sense classically.
But quantum correlation, entanglement, is stranger. Imagine two quantum particles linked. Their fates are intertwined no matter how far apart they are. Measuring one instantly tells you something about the other.
This is the spooky action at a distance Einstein worried about.
That's the one. Schrödinger, who coined entanglement, was also deeply troubled by it, led to his famous cat paradox, simultaneously alive and dead.
Because the cat's fate was entangled with a quantum event.
Exactly. And the EPR paper, Einstein, Podolsky, Rosen, argued this instantaneous connection meant quantum mechanics must be incomplete. There had to be hidden variables explaining it locally.
Like pre-programmed instructions.
Sort of. Prashant uses the example of two entangled electrons with opposite spins flying apart. Measure one as spin up.
You instantly know the other is spin down, no matter how far away, faster than light.
It seems like it. But John Bell's work and experiments verifying Bell's inequality showed quantum mechanics is right. These non-local correlations are real. No hidden local variables can fully explain them.
So you know the state of one by measuring the other without touching the first one.
Right. And this entanglement, combined with superposition, is where the massive computational power potential comes from. They work together.
Prashant uses the Bertelsmann socks analogy in 2.5.1.
Yeah, Bertelsmann always wears mismatched socks. See one, know the other. Simple correlation.
But the difference with quantum entanglement
is the measurement choice matters. With socks, the colors are fixed. With entangled particles, what you choose to measure on particle A affects the correlated state of particle B. It's not predetermined in the same way.
Section 2.5.2 dives deeper into EPR, hidden variables, Bell's theorem.
Bell showed that if local hidden variables explained entanglement, the correlations would be limited by his inequalities.
But quantum mechanics predicts correlations stronger than Bell's limits.
Exactly. And experiments confirm it. Quantum mechanics violates Bell's inequalities.
Meaning local hidden variables can't be the whole story.
Correct. Assuming locality that measuring particle A doesn't instantly affect distant particle B, then local hidden variables fail. Bell's theorem basically says no local realistic theory can reproduce all of quantum mechanics' predictions.
It fundamentally challenges our classical view of reality, locality, causality.
Deeply. Which leads nicely to section 2.6, quantum teleportation and quantum theory of information. The idea that information is physical.
Not just abstract zeros and ones.
No. And processing information uses physical means. This opens up quantum information theory, new logic gates, secure crypto, denser storage, and teleportation.
Not like Star Trek, presumably.
Heh, not quite beaming Scotty up. Classical teleportation would scan, transmit info, rebuild a copy, destroying the original. But quantum mechanics, via the uncertainty principle, says you can't perfectly scan an unknown quantum state classically.
Can't know everything about it perfectly.
Right. But quantum teleportation, proposed by Bennett and others, uses entanglement. You can transfer the exact quantum state of a qubit from Alice to Bob without physically moving the qubit.
How does that work, basically?
Alice has the unknown qubit. Alice and Bob share an entangled pair of qubits. Alice performs a joint measurement on her unknown qubit and her half of the entangled pair. She gets 2 classical bits of information from this measurement.
Right.
She sends those 2 classical bits to Bob through normal, slower-than-light communication. Bob uses those bits to perform a specific operation on his half of the entangled pair, and poof! His qubit transforms into the exact state that Alice originally had.
Wow. But it's not faster than light communication.
No, because Bob needs Alice's classical message, which travels at or below light speed, to complete the process. It's the quantum information that's teleported, instantaneously correlated via entanglement, but activated by classical info.
Still amazing. Okay, section 2.7, thermodynamics of quantum computation. Computers generate heat.
They do. Laws of thermodynamics apply. Prashant discusses Landauer's principle. Erasing information must generate a minimum amount of heat related to entropy increase.
You can't get around that.
Fundamentally, no. But quantum computation, except for the final measurement, can be reversible.
Meaning?
Meaning, in theory, an ideal reversible computation doesn't have to generate heat during the process itself, only when you erase information or measure. Reversible gates, like the Toffoli gate, exist. They keep all the information so you can run them backwards.
So potentially much more energy-efficient computation.
In principle, yes, though real-world implementations still have heat from resistance, etc. And reversibility often means storing lots of intermediate data.
Trade-offs. Then section 2.8, experimental realization. How are people actually trying to build these things? It sounds hard.
Extremely hard. The concepts are tricky, quantum states are fragile. But Prashant outlines several promising approaches.
Like what?
Heteropolymers, ion traps using lasers to manipulate ions, quantum electrodynamics cavities with atoms and photons, nuclear magnetic resonance, NMR.
NMR sounds familiar, like MRI.
Similar tech, using nuclear spins in molecules as qubits manipulated by radio waves. NMR has actually achieved some of the most practical quantum algorithm demonstrations so far.
What else? Quantum dots.
Yes, tiny semiconductor structures trapping electrons. Qubits can be electron spin or charge. Easier architecture maybe, potential for electrical control, but challenges with readout and connecting distant qubits. Also Josephson junctions using superconductors. The Kane computer using phosphorus and silicon.
A whole zoo of approaches.
And then topological quantum computing, using exotic anyons in 2D systems. Qubits encoded in the topology of how they're braided could be inherently error-resistant.
Braiding particles. Sounds wild.
It is. Very cutting-edge theory.
So, section 2.9, future directions. Where does Prashant see this going?
Well, the foundations are there, but lots more needed. New algorithms, better error correction, controlling decoherence, that interaction with the environment that kills quantumness, advancing the tech, finding real-world applications.
What kind of potential does he mention?
Using reversibility for hard NP problems, interference for optimization, quantum tunneling for simulated annealing, using complex numbers in new ways, even ideas from quantum field theory.
Big challenges remain, though.
Huge ones. Understanding many-body entanglement better. Understanding decoherence and measurement itself, they're not fully understood. We need a unified picture. How does the quantum world transition to the classical world we see? Maybe there are limits to quantum theory we haven't found yet.
So theory and tech have to advance together.
Absolutely. Shifting from just observing quantum effects to actively controlling them for computation, the future is promising, he says, but definitely uncertain.
Okay, that covers the main survey. But then Chapter 3 offers a new outlook to the principle of linear superposition. Prashant proposing a modification.
Yeah, this is interesting. He suggests adding an explicit correlation term, delta, to the standard quantum description, specifically for entangled EPR-like situations.
So the wave function isn't just a sum of individual states anymore.
In his proposal, for entangled systems, it's alba plus the usual sum, plus 0, 1.
And based on this delta, he categorizes systems.
Right. Core 0. Purely unentangled, good for algorithms. 0 core 1, mixed entanglement, maybe tricky for computation. Core 1, purely entangled. Tor term dominates, the sum part is 0. Maybe better for teleportation.
Does this fit with the basic equations?
He argues it's consistent with the time-dependent and time-independent Schrödinger equations. It's a conceptual proposal.
And section 3.2, an alternative interpretation of quantum no-cloning theorem. We know you can't copy an unknown quantum state. Why?
Standard reason, measurement disturbs it. Uncertainty principle, wave function, collapse.
The Prashant offers another angle.
He suggests it might be fundamentally linked to information loss and irreversibility during measurement, connected to thermodynamics, the second law. The fact that conjugate variables like position and momentum don't commute, A, B, 0, also implies irreversibility.
So irreversibility makes cloning impossible.
That's his alternative idea. He even wonders if we need a new parameter, like entropy, for the choice of information in measurement. It's less about uncertainty, more about irreversible information choice loss.
Fascinating perspective. Moving to Chapter 4, back to experimental realization, focusing on materials of low-dimensionality quantum dot as a promising candidate.
Right. Referencing Feynman's vision of nanoscience, Prashant notes nanomaterials keep basic properties down to the Compton wavelength scale. Below that, things change. Energy levels shift, nanoproperties emerge.
Why is that scale important?
It's where quantum effects really dominate for the particle, like an electron. Moving to nanodimensions confines electrons, makes them behave more like electrons and atoms. Quantum wells, 2D, wires, 1D, dot, 0.
And quantum dots are promising because
their zero-dimensional nature limits interaction with the environment, potentially reducing decoherence compared to other methods. Fewer ways for the quantum state to leak out.
makes sense. But Section 4.2 raises a problem. Need for modified Coulomb potential. What's the issue with the standard one?
The standard Coulomb potential, 1R, blows up to infinity at zero distance, leads to infinite energy, fields, mathematical problems in classical and quantum electrodynamics.
Things aren't really infinite in reality.
Exactly. So people try to fix this. Renormalization is one complex way. Prashant discusses a different approach. Modify the potential itself classically, so it's regular finite at R00, then quantize that.
How?
Following Prof. Y.M. Gupta's ideas, keep Maxwell's equations, use a potential that's finite everywhere, no new arbitrary parameters, matches classical physics at large distances, Bohr correspondence, applies generally. The core idea is to avoid the singularity from the start. He gives a specific mathematical form involving the sine integral function, psi.
Okay, a divergence-free potential. How does he apply this in Section 4.3? Analysis of quantum dots using modified Coulomb potential.
He models the quantum dot like a hydrogen atom, but uses this modified potential. Inside the dot, especially near the center, within the Compton wavelength scale, the potential behaves more like a harmonic oscillator, Coulomb Panadar. Outside, it transitions back towards the standard Coulomb form, -1.
Why harmonic near the center?
It reflects the strong confinement. He notes there's some experimental support for this harmonic behavior at very short distances. By matching the potential forms at the boundary, Compton wavelength, he can estimate parameters and solve the Schrödinger equation for the electron state in the dot.
And he suggests a link to the uncertainty principle.
Yeah, a thought-provoking idea that maybe this harmonic nature at fundamental levels is related to the inherent uncertainty in position and momentum. He also shows a graph of the resulting wave function.
Then Section 4.4 extends this to study of quantum wires, 1D systems.
Same modified potential, but now the electron is free to move along the wire, say the z direction. Using Mach techniques, variable separation, the solution for the z-direction part of the wave function just comes out as a free particle.
Which makes sense, it's not confined along the wire.
Exactly. The analysis is more complex than for dots, but he again stresses the Compton wavelength is key. It seems to be a fundamental scale parameter.
And Section 4.5 gives a real-world touch. Visit to the nanotechnology lab.
Yeah, a nice practical counterpoint. Seeing fabrication, learning about AFM, STM, X-ray diffraction, the tools used to see and make these tiny structures.
AFM and STM use quantum tunneling, right?
Yes, electrons tunneling across a tiny gap. He got to operate in AFM, see images of quantum dots. It grounds the theory in the reality of lab work, understanding 2D wells, 1D wires, 0D dots. He even includes some AFM plots from the lab.
Cool. Finally, Chapter 5 looks at future directions of research, again, but more speculatively. Section 5.1, explanation of measurement problem by symmetry breaking.
This is deep. Can the mystery of quantum measurement, why we get a definite outcome, be explained by symmetry breaking? He links the irreversibility of measurement, implied by non-commuting variables, to symmetry principles.
How does symmetry breaking cause a measurement outcome?
The idea is the observer's choice of what to measure breaks an underlying symmetry, forcing the system into a specific state, eigenstate, corresponding to that measurement. It's not just information loss, but an active choice. He repeats the need for that new choice of information parameter, maybe like entropy.
Needs more research, obviously.
Definitely. How exactly does symmetry break in wave function reduction? How does it relate to Heisenberg uncertainty? Open questions.
Section 5.2 discusses EPR correlation again. Interacting Hamiltonian V's nonlinear wave function. Two ways to model it.
Right. Either change the energy interaction description, the Hamiltonian, or change the state description, the wave function. Prescient's earlier work focused on modifying the wave function, adding.
And the alternative.
He suggests future work could explore modifying the Hamiltonian instead, adding a potential term for entanglement. He even wonders if EPR states might slightly violate the strict linearity of superposition, requiring terms like his dou.
Very interesting. Section 5.3 gets really out there. Possibility of third paradigm in quantum mechanics.
Yeah, quite speculative. He reviews classical mechanics, deterministic, can know X and P precisely. Then quantum mechanics, limited in determinism, can know X or P precisely, but not both via Heisenberg uncertainty.
And his proposed third paradigm.
Complete indeterminism. You can measure neither position X nor momentum with arbitrary accuracy simultaneously. A fundamental limit on both.
What would that even mean?
It would require totally new math, new Schrödinger equation, new uncertainty principle. He speculates maybe standard QM is just a special case of this deeper theory. And he throws in a reference to Hawking linking consciousness and the observer effect. Maybe this third paradigm connects there. Highly speculative stuff.
Definitely food for thought.
Yeah.
And section 5.4 is the final conclusion and future scope.
Basically summarizing the whole journey. Foundations established, but huge areas need work. Algorithms, error correction, decoherence, tech applications, understanding entanglement, measurement. The list is long.
But the potential remains huge.
Enormous potential for NP problems, optimization, simulation, new algorithms. He reiterates the need for a unified description of measurement decoherence, studying the quantum to classical transition, maybe finding limits of QM itself, and the crucial link between theory and tech, moving towards controlling quantum phenomena, promising but uncertain.
So after this incredibly deep third dive into Prescient's article,
wow,
we've journeyed further into the history, the principles, the potential, revisited classical limits, superposition, entanglement, the challenges, the possibilities, hopefully even more aha moments sparked for our listeners.
It's truly fascinating how this abstract theory from the early 20th century is now poised to potentially revolutionize computation and information in the 21st. The implications for cryptography, medicine, materials, they're just vast.
And Prescient's review touches so many layers. From philosophy of measurement to hardcore engineering hurdles, we really encourage listeners to dig deeper into whatever sparked their interest. Was it breaking codes, teleportation, the nature of reality itself?
It's a field with so many angles, and as the report shows, the future depends on merging science and technology, understanding and control. Makes you wonder what else about nature we're just beginning to grasp and harness.
Absolutely. Well, if you found this third deep dive into quantum computing fundamentals as intriguing as we did, and you want to stay connected for more explorations of complex, cutting-edge topics,
you know what to do.
Please make sure to subscribe to this YouTube channel. We've got many more intellectual journeys planned, and we definitely don't want you to miss them. Thanks again for diving deep with us.